There we go. Audio's back. Red 546. How's it going, buddy? We actually got the programming stuff working today, which was nice. Sky Life, nice to see you. So we've got the nice Mr. Rogers cardigan today, because it's a wonderful day in the neighborhood. Won't you be my neighbor? We're gonna have a wonderful day today. We've got a lot of stuff. I found my little drawing tablet thing, so I can do drawing stuff as well. I forgot how this works. Page, style, plane. There. Yeah, I've got the drawing stuff, and then I've got the programming stuff. Yeah, should all work out pretty well. I had to do a lot of scraping of stuff, make sure I wasn't... I still might release some information, hopefully not too much. But hey, we'll see. Alright, so what do we have today? I should probably change my stream title or something. What does it say now? It says, Teaching Ideas, CUDA Programming by Example. There we go. So we're going to learn some GPU programming today, except we're actually going to do some GPU programming. I figure that's probably the best thing to do. But hey, first of all, audio's not going to work on that, is it? Every time I unplug the mic, it messes everything up. Okay, so like I said, we've got a lot of fun toys today. We've got the drawing tablet again, and we've got an actual terminal where we can actually start writing some code. So before we do any of that, we should probably talk a little bit about CUDA programming. That may or may not be important, especially if we're going to be learning about GPU programming. So what do we need to know when we're doing something like GPU programming versus CPU programming? So first of all, what's the big difference? So when we're doing CPU programming, when we write code, even if it's run in parallel, which there's a lot of behind the scenes parallelism in CPU code that we don't actually see. It's this thing called instruction level parallelism, where your CPU is actually executing a bunch of different instructions at the same time through this thing called superscalar architecture, which basically says at any given moment I can send multiple instructions out to start work. I've got multiple different pipelines to choose from to send work to. That's something that's completely and absolutely invisible to the programmer, versus something like threads, which is this higher level thing that is completely visible for the most part to the programmer. So but what is a CPU actually meant for? So CPUs don't have a ton of threads. They've got very powerful threads where they can run, very complicated things, completely separate tasks. So when we think of threads, it's important that we don't think of them all equally. It's important that we make some distinction there between what a thread is in different contexts. So when we're talking about a CPU thread, we're going to be talking about these very powerful things. When we talk about a GPU thread, we're talking about these little itty bitty things that, they basically just get told what to do. They have they have a fairly large amount of state, but that's just because they're doing a fairly large amount of computation. And their state is basically just their private register file. So the big difference between CPUs and GPUs overall is that when we're talking about GPUs, we want to go somewhere very quickly. So the analogy is usually, if I want to get from, say, the East Coast to the West Coast in the fastest amount of time by land, you take some kind of sports car and you'd race across. That's great if you have two people that you want to ferry from one side to the other. Now, for GPUs, the example would be a bus. So you'd load a bunch of people onto a bus. It would take, a fair amount longer than it would a sports car, but at the end of the day, you transported 50 people, or depending on the size of the bus, maybe 100 people from, point A to point B. And so that's exactly what we're doing on GPUs. Now, in order for the hardware to be feasible for GPUs, a lot of these ideas of parallelism behind the scenes, they have to be brought up. Otherwise, the hardware just becomes way too complicated. So when we're writing GPU code, we have to be a lot more explicit about what we're doing. So this means things like managing memory. We have to be specific about that. We don't get a lot of leeway as far as making sure that we don't run out of bounds. We have to do a lot of checking for the exact GPU that we're running on. In this case, we'll be running on, I don't know what the default is, but it'll either be a Volta Titan V GPU or a Pascal Titan X GPU, and I think there's some terrible K620 Nvidia Maxwell GPU. He might crush your bus with the data. Yeah, that tends to be a problem. That's one of the things. So a bus, if some people here are unfamiliar, typically refers to basically the interconnect between different components in something like a CPU. Now, one of the problems is that while single core performance has been going up and up and up and getting better and better and better, things like interconnect bandwidth and interconnection networks in general, they have not scaled the same. So just because you have cores that are, say, 4 times the performance, that doesn't mean that you shove 4 together. Even if you have a 4x parallel task, that doesn't mean you're going to get 4x the performance. You have a lot of these hidden overheads. But we'll discuss a lot of that. So let's talk a little bit about GPUs, and let's talk a little bit about how GPUs work. So the first thing we need to understand is how things get composed, right? So we'll start out with this single idea of a thread. So for simplicity, we'll just say a thread executes instructions. Very basic, naive. It executes instructions, and then it has some state. Now, this state, you can just consider it, some private storage, so something that only it can see, which is common. So in this case, we'll just call it, registers. Now, how are threads grouped inside of a GPU? Well, in Nvidia GPUs and even in AMD GPUs, the idea is the same. They just have different names. So in Nvidia GPUs, they get bundled together in this thing called a warp. Now, a warp is a collection of 32 threads. And so what happens when you're executing a warp is that every single thread within that warp is executing the same instructions. So they're on the same program counter, so all 32 things are doing the exact same instructions. So if we have, say, add B and C and store it in A, then all this would be 32x this. So we'd have 32 instructions all going at the exact same time. They're all in the exact same place. Now, we'll just leave it there for now. Keep it very simple. We'll just assume that, hey, at any given moment, they will all be doing the same instruction. And for a lot of the stuff that we'll be doing, they will be doing the same instruction. There is this idea of warp divergence where if you have, say, control flow, so if you have an if statement that only some warps will go this way and other warps will go this way, then this doesn't quite hold up. But there's this thing called an active mask, which basically says, okay, you 16 threads progress down this way, and then eventually, after they get to some reconvergence point, the other guy goes, okay, you 16 threads go through this way, and eventually they all line up again, and they all proceed together again. So that's the basic idea. Now, a warp is the smallest schedulable thing on a GPU. So on a physical hardware level, when we're moving things around or executing things, the smallest granularity that we're going to see is a warp. There's coarser grain granularities, but we're getting to that. As you can see, we're kind of building this up. So we started at a thread, we got to a warp, and so now we're going to get to, I don't know if this will actually, oh well, okay. So then we have a thread block. So a thread block is something that we use in the actual programs themselves that we write. So when we're writing our actual code, we don't think of things in terms of warps. Now we should size things so that they are, so that it's scaled number of the warp size. So if we have a problem that we want to launch, it should be a size that's, modulo 32. So it should be something like 64, 128, 256, and so on and so forth. That's just so that we always have all 32 threads active. Now, we pack all of these warps into things called thread blocks. So we'll have inside of each of these things, we'll have, so these things will be made up of warps. And remember, each of these things will have some threads in them. So the final level, after we get that, so this is when we start actually getting to the programming level. Then we have one final thing, which is going to be grid size. Now, what's our grid size? Our grid size is going to be just a collection of thread blocks. So we'll have, a number of thread blocks that we want to launch. This can be 2-dimensional, it can be 3-dimensional. It might even go back this way, where we'll have, thread blocks, in a 3rd dimension back here, right? It's the exact same idea though. A lot of times we just use grid size as well, so this is also at the programming level. So when I say programming level, I mean this is something that you directly, when you call GPU code, you give it a thread block size and you give it a grid size. So, these are the ways that we scale the number of threads that we launch. So when we say we want to launch a GPU kernel and execute some GPU code, we say how many thread blocks are we launching, and then what are the size of the thread blocks. Okay, pretty simple. but still a lot to take in. So let's run through it again. So we have threads. Threads execute instructions, and they have some small amount of state related to them. Threads get grouped into something called a warp. Warps are just collections of 32 threads, and they all execute the same instruction at a given time, mostly. We'll ignore the nuance for now. You can think of them as kind of running in lockstep. So at every given step of the clock, they're all doing the same thing. Then we take these warps and we throw them into thread blocks. So thread blocks are something that are at the programming level, which means that we get to assign a size to them. So we get to say, hey, you're a thread block, you have a single thread. Or we say, okay, you're a thread block, you have 1024 threads or 2048 threads. This is something that is generally limited by the architecture, and it's something that you can find in if you look at the white paper for something like the Volta architecture, it will tell you what's the max thread size or thread block size, what's the max grid size. So then we get into grid size. Grid size is just the number of thread blocks that we're actually launching. So when we're talking about the number of threads within a thread block, that's our thread block size. When we're talking about the number of thread blocks, we're talking about the grid size. So that's the introduction to, a lot of the things that we're going to be working with as far as what's actually going on the actual GPU. So how does thread block translate to physical threads on the GPU? So thread blocks, so everything is sized on the GPU based on max thread block size and warp size. So the actual threads that are getting executed, the actual lanes of execution, that's going to be this warp size. So things will be 32 wide when you start getting down because the minimum size of execution is 32 threads at a time. So when you actually look at a streaming multiprocessor, which is what you can think of as the core of a GPU, the cores have they have warp schedulers in them. So they'll schedule a warp and it'll execute warps. So thread blocks themselves is just a higher level programming abstraction. So thread blocks, you basically just say how many threads go into a thread block. When that actually gets launched on the GPU, when that actually gets launched, it'll have some amount of threads, and then that will get broken up into warps. Right? So if you launch a thread block that say has 128 threads in it, it will have 4 warps. So those 4 warps will be when that thread block gets assigned to a core or an SM. That's when those warps will get scheduled by the SM schedulers on that core or SM. Okay, so this is kind of the base level that we need to know in order to understand how does what are we actually programming when we're talking about how do we launch threads. So this is what we need to be thinking about. And so when we're talking about the actual programming side of things, it's just thread block and grid size, and then the important thing to know here is that this is going to change per GPU. Now, technically, warp size could change per GPU. However, Nvidia's kept it constant, I think, forever at 32 threads, and then AMD, I think, has also kept it constant, but at 64 threads. Now, theirs isn't called a warp, it's called a wavefront, but it's the same idea. Like, I think in Nvidia, these things are called wavefronts, and then thread blocks are called maybe schedulable entities or something. I'm not very familiar with Nvidia or AMD GPUs, but the concepts are the same. AMD is better than Nvidia. It depends. In some aspects, yes, and others, no. Nvidia hardware is, I think, always better than AMD hardware, and then there's no comparison between Nvidia software and AMD software. Nvidia software is just far and away better. But if you're talking from like a price comparison standpoint, AMD usually does better, and then I don't think Nvidia even tackles the APU system where it's a integrated shared memory GPU CPU on the same chip. That's something that I don't think Nvidia has a single product line of. So in that respect, you know, AMD absolutely is better than Nvidia because Nvidia is not even competing. Okay, so anything else before moving on? Wait, there's a way to just add a page, isn't there? Oh, it's probably up here. Yeah, there we go. Okay, so that's the high level. That's what we're going to be programming. Proprietary stuff. Yeah, it is proprietary stuff. Unfortunately, though, it's the only language that people use to program GPUs. Nobody uses OpenCL for GPUs, just because it's way worse. AMD doesn't, but nobody uses AMD GPUs for this kind of stuff. I mean, there's a reason why. What's it called? There's a reason why Summit, the supercomputer from the U.S. National Labs, bought 28,000 Volta GPUs to put in there. It wasn't because they liked Nvidia more, even though they did get a good deal on the GPUs. The reason was because that's what's usable. I'm assuming AMD is working with Intel to take on Nvidia for OEM systems. Yeah, maybe. I mean, I don't really know much about it. I mainly stick to my field. I mean, it's more competition inside the area of GPUs and GPU programming, and not just having Nvidia be the end-all be-all is, of course, something that's very attractive. Hey, Lev, how's it going? It's nice to see you today. Okay, so let's see, what else do we need to cover before we start programming? So we covered this concept of, I won't belabor this point, but we covered this concept of having threads being grouped into warps being the lowest schedulable entity. Then we have our programming level of abstraction where we have thread blocks, and then the number of thread blocks we launch depends on what we classify or what we have as our grid size, which is just each of these things is just an individual thread block, right? So then behind the scenes, all these threads get converted into warps, right? So we don't program at warp level, we program at thread block level. And then we say, okay, you go off there and split it up into warps somehow. I don't really care. Thread block is really the important thing because we actually get more state here. So per thread block, there's a couple more things that start coming into play. So there's the idea of shared memory, which is basically like a user-managed L1 cache. So most of the time you have an L1 cache, right? It's completely invisible to you. It exploits locality and makes things run quickly, but you honestly don't look at it. In GPUs, this is very different. So there still is an L1 cache and there's an L2 cache, but it also has this shared user-managed where if you know that you're going to be using this data over and over and over and you don't want it to get potentially kicked out, you load it into this user-managed cache, and that's called shared memory, right? And so we'll go into that at some point. So let's see, what kind of problems do we want to tackle? So there's a lot of problems. What we're going to start out with is a very simple one, right? So whenever you start programming any language, you generally program something like this. You do C is equal to A plus B, right? Works great for sequential. You only need a regular processor because it's, a single element. These can be integers, these can be floats, These could even be doubles, right? It could be any of these things. But like we said, it's, single element, doesn't take up a lot of space. It doesn't really make sense to run it on GPU. GPU is just going to be slower, especially because we have to do all the setup first and then launch something. We want to tackle parallel tasks. So we're going to write probably the most common benchmark that we know, which is vector add. This is the hello world of GPU programming. So what is vector add? It's exactly what it sounds like. It's vector addition. So instead of, doing A plus B or A plus B equals C, we're going to do, here's some vector C, and it will be the sum of two other vectors. Now, this is what we call an embarrassingly parallel task. Matrix multiplication we'll get to a little bit later. Matrix multiplication is a very, very helpful way to motivate the need or motivate the use of shared memory. And we'll see that through something that's a more advanced concept in CPUs, which is this idea of tiling. But we'll see that it's an absolute necessity when we start writing code for GPUs. So why is this embarrassingly parallel? So this is embarrassingly parallel because every single operation is completely independent of one another, right? So element 0 in all of these has absolutely no bearing on what happens when we add element 1, which has absolutely no bearing on element 2, which has absolutely no bearing on element 3. It's all completely independent, which makes, it's a very great example program to actually have on a GPU. So what are we going to be doing? So we're actually going to write a simple vector add program. We're going to compile it. And so that's what we have right here. So I'm just using Vim. I like using Vim. But very simple. The extension is going to be .cu for a CUDA file. The only requirement is having a CUDA-enabled GPU and having the CUDA toolkit installed. So that's just going to be, you need the driver and you need the compiler, which is NVCC, which is basically, Nvidia's compiler for the GPU code, basically put on top of GCC. So if you have GCC, you can just link against the CUDA runtime library and it'll work, right? So a lot of times you don't even have to see NVCC used. A lot of times you just see GCC or G++ used. So this is also a time, if you have any programming questions, you can get those out of the way. There's no reason to be shy about that. We'll see that GPU programming doesn't have to be that difficult, and often GPU code is very small, right? So let's get started. So we'll just call this my first GPU program. Very simple. So, as always, we're going to need a main function. And it's useful to include a couple things. So, what are we going to include? So, we'll include stdio.h just so we can print things out. A lot of times it's useful for debugging and as well as seeing your results. And then we want the standard library because we want to use something like Malloc, right? When we're working with things like arrays, we could use that as well. You could also use vectors as well, so you could include vector instead. For this, we'll just keep it super simple, and we'll just use the standard library. Is this big enough, the terminal? I don't know if it's actually big enough. Let me see what it looks like on my end. Well, it looks okay. All right, so, all right, that's good. I was hoping it would. So, what do we need to do first? So, let's just give it a an input size, right? So, we'll just use an integer number of elements for a vector. So, we'll say n is equal to, let's use a meg, right? So, we'll just do int n equals 1 meg. So this will actually be 4 megabytes of integers, right? So we're working with a lot of elements here. So right, so this would be, so to put this in perspective, 1 to the 10 is going to be 1024. So 1 to the 20 will be the equivalent of, you know, an order of magnitude up, right? So you'll have like a meg, a gig, or a 1K, a meg, a gig, a terabyte, and that's generally 10 to the 10, 10 to the 20, 2 to the 10, 2 to the 20, 2 to the 30. So this is a pretty reasonable number. So this will be just our number of elements. So what should we have next? Next is going to be pretty simple. We're just going to start specifying, you know, very basic stuff. So we'll do this on integers. So we'll have a host A, host B, and a host C vector, or not a vector, an array. And then we might as well specify our device. So we can just call these our host pointers, and these will be our device. Oops. These will be our device pointers, and so they'll still be integers. It's important to note that because we have CPU memory and GPU memory, these are two completely different things. So a GPU is going to have its own physical memory associated with it. So we can't dereference pointers from the CPU on the GPU and vice versa. By host you mean CPU side, right? Yeah, so when we're talking about the host side of things, that's going to be the CPU. When we talk about the device side of things, that's going to be the GPU. So we still need to make pointers for all the device side things. And so we'll just give them a convenient name. So H as a prefix for host, D as a prefix for device. So then, like everything, we actually have to allocate. So here we'll just start allocating on the host side. And we do that with the way that we all know, which is malloc, right? Let's actually make a convenient variable that we can reuse. So let's make a type size t. We'll call it bytes, and this will be n times size of int, right? Because we have n ints that we want to add together, and so we want the number of bytes to be the size of an int. So this will be 2 to the 20 times 4, right? So then here all we have to do is malloc bytes, right? Oops, and then can't forget an equal sign. And we'll actually do this for all three, right? So here we have it. We've allocated space for all of our host side vectors. So then we have to do our initialization on A and B. So go. So for this, we'll just do something super simple. So we'll just say, we'll just do 1 plus 2, right? So this could be any random number, so you could initialize this with like a rand function or something for simplicity, and just for ease of checking. We can just verify that this is 3 at the output, right? And remember, we don't need to initialize C because C is going to be computed by the GPU anyway. So pretty simple so far. We haven't done much. All we've done is allocate some space and initialize a couple of vectors. So now we get to the actual GPU side of things. So now we need to allocate memory on device side. Now, if you guessed that we were going to use Malloc again, you'd be almost correct. So we're going to use CUDA Malloc this time. So CUDA Malloc is an extension to the C language, which basically just says we're going to malloc, but instead you're going to send this off to the GPU for the GPU to start allocating space, right? So here we'll do CUDA Malloc, but it's exactly the same. So in this case, we're going to pass in the address of the device pointer because it's going to fill it with the pointer to device memory, right? So device memory has its own address space, its own pointers, and so we basically need to fill our pointer with the address in device memory. So that's what we're doing right now. And then it's the exact same, so the other argument is just going to be how many bytes we're going to be allocating. So pretty simple. And we'll just do this with all 3. So so DA, DB, and DC. These are all the exact same size. Any questions on any of this stuff? It's fairly straightforward. It's just another malloc. All right. So then we need a grid size and we need a block size. So remember, block size is going to refer to the number of threads in each block, and our grid size is going to be the number of blocks that we're actually going to be launching. So in this case, we'll have init block and grid size. Now, a lot of times we just put some this is really a tuning parameter, so it's whatever we feel like putting in here. So in this case, I'll have block size, and then I'll just say that it's going to be 1024. So every single block is going to have 1024 threads. Now, this can change, right? Because in reality, all of these sizes are 3-dimensional. So you can have a 3-dimensional block size, which means you can have 128 threads in the X direction, 128 threads in the Y direction, and then 128 threads in the Z direction. So what's the point of this? The point of this is really for the convenience of the programmer. A lot of times we're working with matrices or things that are parallelizable like that. So a lot of times it's convenient if we can have these multi-dimensional ways of launching threads. That way, when we're trying to reason about what thread is doing what work, we don't need to, say, reduce the dimensionality of it to being, 1 dimension. We can think about it, this direct mapping of 3D to 3D or 2D to 2D. But in this case, we're just going to be working with 1D because we have a 1D vector, right? So we'll do a set block size, and then other than a block size, we need a grid size. So int grid size. Now, if we already know that we're going to be launching 1024 threads per thread block, then it becomes rather trivial of what our it becomes fairly trivial what the number of thread blocks we need to launch is. It's just going to be the number of elements divided by 1024, which is what we'll do here. So we could directly do grid size is going to be n divided by block size, but this isn't terribly smart, because what if we had a non-base 2 or a non-power of 2 number of elements? Well, then we're going to run into some sizing issues. So we have to play this game a little bit smarter, and we'll see that most of what GPU code is making kind of smarter code that can handle these arbitrary inputs. But this isn't terribly difficult to do. So what do we do? Well, first thing we do is we know that we're going to need an integer out of this. And we know that we need to add extra space just in case, which means we're probably going to be using something like a sealing function if we have a remainder. So, which is exactly what we're going to do. We're going to use a sealing function. And so what we're going to do, we're going to take the sealing of this division that we're going to cast as a float, right? So what's going on here? We're saying, okay, take our number of elements, divide it by 1024 threads per thread block, and then if we have, say, 1025 elements and we're dividing by 1024, the sealing function is going to give us 2 because we're going to get some small remainder. It'll be 1.00 something, right? So this is just for the sake of simplicity. If we always knew that it was going to be a power of 2, then we could just simply do in divided by block size. So we can print this out. So printf, and we can say and then we'll just put in grid size. That way we get a nice print. Okay. Any questions on any of this stuff so far? All right. So, quick run through. We allocated memory on both the CPU and the GPU. We calculated the number of threads that we want to launch. Each of these threads will be doing independent work. And now we get to the final point where we actually we need to have something to run. So we need to write the actual GPU code side of things. So now we can go back up to the very top and we can do that. So when we're writing a GPU kernel, it's called a kernel because it's typically the small inner loop of something that we want to parallelize. So it's a small kernel of an entire program that we want to run on the GPU. So we'll start out with this prefix, global. There'll be a void function because it's not going to return anything. I think the only return type for a GPU function, because they're completely different address spaces and having a return type doesn't make sense really. I think the only return type is a error message. I think it's just like a CUDA error T object, which will just say if it completed successfully or not. So then, we'll just call this vector add, right? And so what are we going to pass in? So we're going to pass in some pointers, right? And these will be the pointers to device memory that we're going to be accessing. So we'll just say this will be a pointer to A, a pointer to B, a pointer to C, and another just integer, which will be the number of elements that we're going to be computing, right? Other than this global, it really looks like any other function. Now this is where it gets a little bit different. This is where we start thinking about, okay, well, how does each thread know, where it is or what element of the vector to actually work on? So this is fairly simple as well. There's per thread, there's information built into it. Right? There's information built into each thread, so it knows who it is. So it knows things like, okay, what block am I from? So which thread block am I coming from? And then it also knows which thread within that thread block am I. So down here we specified every thread block will have 1024 threads, right? So if we know that every thread block is going to know, okay, I'm thread block 1, I'm thread block 2, I'm thread block 3, and then every single thread knows I'm the first thread of thread block 1, I'm the second thread of thread block 2, I'm the 219th thread of thread block 3. That means that we can do some pretty easy base offset calculation to figure out of all the threads, who am I? And so that's this typical thread ID calculation that we do in here. So in this actual GPU code section, it'll just look like C++ code. So we'll have int, we'll call this TID, typically stands for thread ID. And what we're going to do is we're just going to use these internal variables. So first we want to know, okay, what block am I from? So there's a variable called block idx.x. Now, like I said, all these things are three-dimensional. A lot of times we only use 2 dimensions or even 1 dimension. In this case, it makes sense to just use, say, the x dimension because we have a linear array of elements. So we have block idx.x. We'll multiply this by the block dim.x. And then we'll add the thread idx.x. Now what's going on here? We can take a small break over here. We can do a little bit of drawing, right? So if we have this big long train of elements, right? And let's just say this is going to be block 0 and this is going to be block 1. So let's say this is element 0 is going to be over here, and then because we said that each one of them has 1024 threads, this will be 2047 over here. So 0 to 2047, 2048 threads. Now, what does this actually look like? So if we want to get any individual thread out of here, all we need to do is a very simple calculation. So we know that this is going to be 1024 total, and we know that this is block 0. So what do? We do this exact calculation. So we get the block ID. So in this case it will be 0. We get the block dimension, which is 1024. Oops, that's 24 needs a 10. And then we add the individual thread ID. So in this case, if we wanted to access thread 38, thread 38 would know that it's thread 38, right? So every thread is going to end up knowing exactly who it is. And let's say if we want to access something in block 1, this calculation is still exactly the same. This 0 just turns into a 1, so our block ID is now 1 over here, times 1024. So that means we're going to be starting right here. So we're going to be starting at the start of the block, and this is just a very simple calculation in order to take, take these vectors and break them down into their individual threads and how we're actually calculating who's doing what work. Any questions on that kind of indexing? So that's all this calculation is doing. It's basically just a base offset calculation. And if you started doing 2D stuff, you see that this becomes exactly the same. You just end up with a 2-dimensional version of this. So the only thing that changes is you start needing to calculate the row as well. So so you calculate which row, and then you calculate what's your offset in that row. So it becomes pretty much exactly the same. So let's move on. So now that we have our exact thread, what do we need to do? We just do simple vector add. So what is simple vector add? Vector add is just going to say we're going to do C of TID. So every thread is going to be responsible for its own element. So C of TID is going to be equal A of TID plus B of TID. That's it. That's vector add right there. And we want to make sure that we're a little bit robust, just in case. Just in case we do get a weird input size that isn't, perfectly scaled to the thread block size. We want to just write a quick conditional in here. So we just want to say if TID is less than N. So this just says that if my global thread ID is going to be less than the total number of elements, right? This just makes sure that if we have, say, let's say I said we have 1025 elements that we want to process stuff on. So then what would happen is I would still have two blocks, but in this block over here, I would only have a single thread, right? So this would be 1024, and then this would just be one thread. Now, in the background, we'll do this in yellow, so it's a little bit transparent, or we'll just do it in green rather, so you can actually see it. So in the background, all of these threads, they still exist. They're still physically there in hardware. We're just saying you don't need to run right now, or you're not important right now. So in the grand scheme of things, these shouldn't do anything. Now, if we didn't have this conditional in here, they'd be accessing out of bounds memory. Now, we don't want them to do that. So what happens right here when we do this, if thread ID is less than N, if we get any number less than 1024, so where's my pointer? There it is. So these will be threads 0 to 1023, and then this will be thread 1024. If any of these threads over here want to run or something, it gets to this conditional and it says, okay, I'm not going to do anything. I'm not going to access any out of bounds memory. This is just part of GPU programming. You have to program, you're basically completely beholden to the hardware. You've got to hold its hand through everything. It's not going to help you at all. Now, what actually ends up happening in the physical hardware is that you'll have all of these slots for different threads, right? And so if this is some program counter count, so if we're at some instruction, what ends up happening is you will only have a single active thread. All of these other threads will be idle, right? So that's this thing called an active mask. And we might get into that a little bit later, but from a very high level point of view, you have to include this in there, otherwise you'll access, if you only allocated 1024 or 1025 integers on the GPU, as soon as you access that 1026 or 1027 space, well, depending on the architecture, something different could happen. So if you're on an older architecture, you'll read garbage. If you're on a newer architecture, then it will just give you a segmentation fault. Okay, so moving on. So now that we have our basic kernel code, this is all we need to do. By the way, this is the entirety of our GPU code right here. GPU code is very small. It's not super huge. It's just that we have to think about the actual threads, which is why it becomes complicated. We have to do a lot more thinking than we normally have to do when we write this code. But all we did was we calculated a thread ID. So this will be calculate our index thread. So basically every thread needs to know where it is, and so we can find the exact position that the programmer assigned to it based upon these values. Then we make sure we stay in bounds, and then after that, very simply, we actually do vector add, right? This is our actual vector addition right here. So we're actually doing 2 to the 20th additions in this one line of code. Pretty snazzy, right? But the difference is we're doing what's it called? we're doing 2 to the 20th additions at the exact same time, or roughly the same time. All right. So what else do we need to do? So we still haven't moved any of our data actually onto the GPU at this point. Everything's still sitting on the CPU side of things. So we need to do a mem copy, more specifically a CUDA mem copy. So that's done with CUDA mem copy. So we're going to have CUDA mem copy. Our destination will be our device pointer for A that we allocated right here with CUDA Malloc. We're going to be copying from our host pointer of A, which we initialized up here. Then the only other thing, we need to say how much or how large of a size. So we want to do an entire vector. So it'll be n times the size of an int. So 2 to the 20 times the size of an int. So we'll be copying a meg of ints. So every vector or array that we're copying over will be 1 meg in size. And then we actually have to specify the direction. So we have to do CUDA mem copy host to device. Right. So we need to say that we're actually taking memory out of CPU memory and we're giving it to the copy engine to put into GPU memory. And so we actually need to do this twice because we need to do this for our B array as well, right? So what do we have next? So then we actually need to launch our kernel. So kernel launches exact same as you'd imagine. So we called it vector add. So we'll just launch vector add like a function. The only difference is we now have this weird triple chevron notation that will just be saying what's your grid size, what's your block size, right? So this will say how many blocks am I launching, which is a variable that we calculated right here. And then it'll ask what are the size, or what is the size of each block, and so that'll just be our block size. Now there's technically 2 other values here, which will be the amount of shared memory that we want to allocate, and then what stream that we're actually launching on. We're not using shared memory right now, and we're not doing concurrency of multiple different kernels, so we can leave those blank and they'll be set to 0 for shared memory and also 0 the default stream. Then all we do is we just use normal type parameter launching for a function. So if we go back up here, we can just split the screen. If we go up here, we see that all we need to do now is we need to give it our A, B, C, and N, right? So this will be device A, device B, device C, and N, right? We need to make sure that we're using the device pointers here because we already allocated these on the device. We copied memory over to the device being the GPU. So we don't want to be accidentally giving these host pointers. If the GPU gets a host pointer, it's going to try to access that host pointer when it does vector add, and it's going to say, what did you give me? You didn't give me anything I know. I don't know where this address is. All right. So pretty simple so far. And this will do everything for us except copy the data back. So we still need to get the data back. How do we do that? It's another CUDA mem copy. So I can go ahead and exit out of that one. So we'll do another CUDA mem copy. This time it'll be the opposite direction, so we want to copy into our host vector this time. We want it from the device vector of C, same size, which is this bytes variable that we made earlier, except this time it will be CUDA mem copy device to host. Right. A little wordy, but gets the job done. There's also a third one. There's a device to device, but that's only if you're running an app on multiple different devices and you actually need to do these like peer-like transfers. Okay, so now we actually have the data back. So we should have a giant meg-sized vector of 3. Actually, it should be 4 meg because we did a meg of elements and every element was 4 bytes, right? Or yeah, 4 bytes. So pretty big. So what do we do? So we should make sure that our answer is correct, right? That's always important. So we'll do that the most easy way we can. So we'll just do another for loop. So this will be all serial. And then we'll just have if it will be host C of I is not equal to 3. We'll just print error. And we should probably also break out of the for loop if that happens. Otherwise, we should just make sure that we'll just say it completed successfully. Right? Oop, there we go. All right. And then let's see what else we have to do. Oh, the only thing we need to do now is a little bit of cleanup. So we want to be good programmers. We want to clear our memory. So we'll just call free on HA. Same thing with the rest, HB and HC. And then if you could guess it, there's going to be another version of free, which will be CUDA free, and we'll just call that on all of our device pointers. So DA, DB, and DC. Let's see. I think that's everything. So we've written our first CUDA program for vector addition, the hello world of GPU programming. And then we did int main. So there you go. Return 0. All right. So what do we do now? So we got to make it. So we'll use NVCC. Our output file we'll just call vector add.out. We'll input vector add into it, and we'll see if it works. Hey, we actually wrote something without any errors the first time. That's pretty good. So we can actually look at the assembly for this if we want to. So there's a utility called, I think if you do --sas on vector add.out, oh, maybe it's -sas. Okay. So if you actually dump this, it will actually give you the this is the actual assembly code that it was generated for the GPU. So this isn't all the assembly code for the entire application. This is just what's going to get executed on the GPU. So all this over here, this is going to be the hex encoding of the instructions, and I think there's also some delays and their delay values put in there. But we can kind of see everything that we did, right? So there's so let's see if we can actually so let's see. Okay, so here we see that we're moving in our specific values that tell us what thread we are. So we see that it in the actual assembly, there's specific values for that. So it knows the block ID, right? So this is just saying get the CTA ID, and this is saying get the individual thread ID, right? And this move R1 from this spot in memory, this is saying get the block ID, right? So because you can launch many, many more blocks that can fit on the GPU at the same time. So the number of blocks is actually something that gets stored in memory. So we get our block ID, we get our CTA ID, and then we get our thread ID, and then we do an integer multiplication and addition. So this is going to be our thread ID calculation. So we have a couple other things in here: an integer set predicate, greater than or equal, and. So this is basically this is our conditional check. So that check we wrote in to make sure we weren't going to reach out of bounds, that's what this predicate being set is for. So then we have an integer scaled add for this. And this is going to set a condition code, I guess. So digging into the assembly, it's going to get a lot more complicated. Your code doesn't look exactly the same, but as you can see, it made some pretty simple looking code. You have to keep in mind that it has to do a lot more memory management and do everything via loads and stores, while we can just say add these two things together. So when we add these two things together, it actually has to get stuff from memory and push it back out to memory when we're done with it. But yeah, this is our application. So then we can see that we compiled it for SM30 architecture. I think it automatically compiles for the minimum architecture. Now keep in mind, when it runs, it will always run on the max architecture. We see that it's CUDA, it's a 64-bit, we're on a Linux system, very simple. And we can actually run it. All right, so it looks like it worked. So like we kind of said before, we did 2 to the 20 elements, and we divided that by 1024 threads per thread block. So 2 to the 20 divided by 2 to the 10 should be 2 to the 10. So we do get our expected grid size of 1024. We can even change the input size if we want to. So we can do vector add.cu again. Oops, it's already open. There we go. So we can do this again, right? So if we want to, we can say this is 2 to the 20 plus 1, right? So this should give us a grid size of 1025. And sure enough, we get a grid size of 1025. We can even scale this up to a gig if we wanted to, right? So let's scale it to a gig. So now every single one of these arrays will be 1 gig in size. Or sorry, it'll be 1 gig elements, right? So it'll be 1 gig times 4 bytes. So pretty big. These things are pretty big. Oops. So we can just make this again. We run it again. Takes quite a lot longer because we just scaled it up by 1024. Oh, looks like something happened. I think we exceeded our size. Yeah. These things don't like it all the time when you, let's just scale it down instead. We probably overflowed something somewhere, so we'll just scale it down and prove that it works there. So now we'll just do it with 1024 elements, which should launch just a single thread block. Yep, so it should just run. Now we can do a more arbitrary input size. So this will be 1024, so there we go. We'll just launch it with that many elements, see what happens. Should work still. There we go. So it still works. Let me make sure that the profiler doesn't release anything. Okay, it doesn't. So there's actually an Nvidia profiler that comes with the CUDA toolkit, and it's called NVProf. So it's the Nvidia profiler. So we can just run this with vector add, and we can look at some interesting stats. Oops, that's the CUDA code. So what do we get here? So we get a couple things. So it'll tell us exactly how long it took copying our for the mem copies to take place. So our mem copy hosted device. It tells us exactly how long it took us to copy back our elements from device to host. And then it tells us exactly how long it took for us to run vector add. Now, as you can see, this probably wasn't really worth our time. So it took much more time copying all these values into the GPU than it did actually computing anything. Now, there's tons of things you can get. So this more motivates just kind of, what problems you should use for GPUs. So if you have to add, say, two 1024 vectors together, you might be better off just doing it on a CPU and parallelizing it with typical CPU techniques. But if you start getting to a meg or a gig, it starts, these kernels typically do a pretty good job. Or the GPUs do a very good job on this embarrassingly parallel stuff. Let's see. So we can scale this back up again to 1 to the 20 again. And then we can run the Nvidia Visual Profiler again on this. It'll take a little bit longer, and we see that, things have started to scale up quite a bit. We're doing a lot larger mem copies, so mem copies are taking in the millisecond scale now. I think we're roughly 10 times what we originally were for our vector add kernel. And then we have all of our CUDA runtime API calls right here. So this is kind of just basic, profiling and not really debugging, but well, you can do some debugging here usually. So if you notice that, hey, say if you didn't write any tests to check your output, and your program ran really quickly, suspiciously quickly. So what could you do? So you could always just run Nvidia Visual Profiler and make sure that your kernel was actually launched. A lot of times people will have a bad launch parameter or something that won't throw a runtime error that will crash the program, and it will just drop through and hit the finishing code. So you'll just go in here and you'll go, okay, well, my kernel didn't run at all. It won't even show up. Or you'll see something like, why are my host to device or device to host transfers suspiciously small? Or why do I have the wrong number of calls? So if I copy two vectors over to the device and I copy one vector back, I should expect two host to device transfers, and I should expect a single device to host transfer. If I have a number other than that, or a number other than 3 total, I probably have a problem. Okay, anyone have any questions? GPU programming, anything that wasn't clear, anything that I need to explain out a little bit more? Let's open the let's see, the Volta white paper. Here we go. So this is what I was talking about earlier. There'll be a white paper for every single architecture, and this will give you all of those parameter values that you might need. So let's try and find some of them. So these are usually important once you start getting to more advanced stuff. So knowing the amount of SIMs you have, so the amount of SIMs, you can kind of count that to the number of cores that a GPU has. So these are tensor processing cores. That's a very specific core that you have to manually specify you're using. Most people don't use them because most people don't know how to use them. I think you have to inline assembly to use them, which is why most people don't. This will just tell you things like the number of floating point units per core. This isn't really the numbers I'm looking for, although it is useful to know your L2 cache size and your memory size. That's specifically for things like cache tiling and making sure you're not, your algorithm is, the working set size is friendly to your GPU L2 or L1 cache size. It's also important to notice that there's a massive shared L2 in these GPUs, or I should say massive, but there's a large L2 that's shared between all of these SMs. However, there's an incoherent L1 cache inside of all of these SMs. So there's a private L1 cache, and then there's a global shared L2 cache. Interesting side note. Large isn't a number. I mean, you can look at the spec sheet, right? Here you go. It's much larger than the L1 cache. But as you can also see, the register file size is much larger than would be on a CPU, right? So 256K per SM. So this 256K times 80 will be the register file size on a Volta GPU. Now that's much larger than is on any CPU. So let's get to the actual numbers that we would need for programming. Yeah, and there's the where is it? Is it on here? Oh, here we go. So we have this 128K L1 data cache and shared memory. So in Volta architecture, these things are unified, which means it's they share the same physical memory. So you have the regular L1 cache that will is hardware managed, so you don't touch it at all, and then you have the user managed L1 cache with shared memory. And then there's texture memory, but a lot of people, no one uses texture memory much anymore. It's much more convenient to just use normal regular memory. Texture memory has some different access patterns that I think people that wrote K-means clustering algorithms used to use the texture cache a lot. It's not really used much anymore. This is some stuff on the tensor cores. Here's the actual table. So as we can see, the number of threads per warp that we talked about earlier is the same on every generation of GPU, at least the most recent generations. But this spans roughly 10 years, I think, if not more. 10 years? 2009? A little more than 10 years. I think Kepler was around 2007 or 2008. We see the max warps per SM is 64, and we see that that's directly related to the number of threads. So 32 times 64 is going to give you 2048. Then what else do we have? The max number of thread blocks per SM. So this says that we can fit 32 thread blocks on a single SM, which means that per SM we can have 32 times 2048 total threads on any SM at any given moment. We have a max thread block size of 1024. Things like max registers per thread. So every thread is going to have 256 registers. So 255 because a 0 register will be there. Yeah, so all of those parameters that we talked about earlier, usually find those in just data sheets like this. And like we said, shared memory size will be per thread block, and it's going to be configurable up to 96K, which means that per SM core, you will have this 128K L1 cache and shared memory. So up to 96K of this can be shared memory. I don't know what the default is though. Or the default, I guess, would be 0 for shared memory, maybe. I don't think they could do that though, because you could inside the kernel. It would have to look in your actual kernel code, because shared memory can be specified ahead of time at launch time or dynamically at runtime. Yeah, but regardless, if you're using shared memory, you know how to specify it, which we'll get to at some point over the course of this. All right, any other GPU questions? Or I don't think anyone had any GPU questions. I think I just kind of rambled on. But yeah, white papers are your friend. Okay. So that's all I have as far as content for today. Next time we can look at implementing matrix multiply using CUDA, and we can probably start looking into what it would look like using shared memory, and so a little more optimization of CUDA code. Instead of just launching mass amounts of threads towards a problem, we can think of, okay, well, how do I increase the locality of the data that I'm using? But other than that, are there any final questions on GPUs or on GPU programming or on GPU architecture that I can answer at this time? Or on anything. I'll answer on anything right now. We've got, have I looked into, let's see, it got cut off. Rapids.ai. Not sure what that is. Rapids.ai. Open GPU data science. Open source software libraries give you freedom to execute end-to-end science and analytics. Relies on Nvidia CUDA primitives. Okay, so it's Python for CUDA. I've looked at a lot of things like this. So there's a lot of libraries that will do parallelization of stuff automatically. So, oh, what's the common one? So the most common thing that's actually done is people use libraries made by Nvidia. So they'll use libraries like cuBLOS, which is a BLOS library. It's a linear algebra library from Nvidia, and it's highly optimized, and it's hand-tuned assembly code, so it's very, very fast, and it's a very easy interface, so you don't have to write all the linear algebra code for whatever you're doing. You can just call a function from their library, give it the input parameters, and it will basically execute the CUDA without you having to write it. The same thing goes with, there's a CUDA FFT library if you want to do fast Fourier transforms. There's all kinds of libraries out there. If you don't want to use the specific NVIDIA libraries, there's other, they're more C++ templates. So there are all these templates out there. So Cutlass is one released by NVIDIA. I think it's just a bunch of C++ templates, but it does the same thing for you, right? It has all these things specified. You just give it some input parameters, and it gets very good performance. Not quite cuBLOS performance, but very good performance. Same thing goes with, I think, the Boost libraries, which aren't from NVIDIA. I think the Boost libraries do the same thing. They're just a bunch of header files, and they basically take your inputs and they do the CUDA for you. That looks like what this is, but it's it looks like that's what this is, but it's for Python. Yeah, user-friendly Python interface. I haven't looked a lot at this stuff, mainly because my focus isn't programming. My focus is understanding the underlying architecture and optimizing the underlying architecture. I typically don't need a higher level abstraction. I generally need to dig in the weeds a lot more. So most of my work when it comes to programming will be writing micro benchmarks to expose certain behaviors of hardware, and then come up with ideas of, okay, well, how do we fix this certain behavior that in this case we see these problems? Or not necessarily problems, but maybe it's a little too slow. Maybe we think that we could do it better. But yeah, that's that's really I think that's a fairly solid introduction to CUDA programming. So as we can see, CUDA programming is not terribly difficult. We see that our actual GPU code that we wrote today is actually quite small. If we look at the actual lines of code, we wrote 1, 2, 3. We wrote 4 lines of code today. That's actual GPU code. 5 if you include the curly brace. 3 if you include just kind of inner block code. But that's how easy a lot of these simple things are. Now, there's always optimizations, so we'll see that with matrix multiplication. And there's also more advanced things we can do with CUDA. So over here, what did we do? We had to manually specify we were mallocing, or we were allocating data on the GPU. Now, it's really convenient if we don't have to say, this is CPU data, this is GPU data. So there's more advanced stuff within CUDA that does that for you. So you can run CUDA Malloc managed, and it will manage the transfer between the host and device for you. So you don't have to do explicit, CUDA memcopy host to device, CUDA memcopy device to host. You may pay an initial upfront cost for that programmability, because it may you may just page fault on the first thing, so you try to access some data and then you it doesn't know where it is at first. So behind the scenes it goes, where's the data? It goes over to the CPU, fetches it, prefetches a bunch more data, maybe it prefetches a couple megs of data of your data, and then for every subsequent computation it's fine. It doesn't miss, all the data's on the GPU. But it provides you this flexibility that instead of having to manually manage, okay, transfer the data from here to here, transfer the data from here to here, it does it behind the scenes. So that's a common thing. It's trading off performance for programmability, but then we want to push it back a little bit. We want to get both. We want to have the programmability, but we also want the performance. So that's what a lot of architecture is. So things like out-of-order execution, right? Something that that's a CPU realm, right? GPUs are completely simple pipelines, right? GPUs don't have any, so there's a reason why GPUs don't have Spectre or Meltdown vulnerabilities. And despite all those clickbait titles you see everywhere that says, could Nvidia be, susceptible for Spectre, or could Nvidia or something be susceptible to a Meltdown style breach? The answer is unequivocally and absolutely no. There's no possible way. First of all, Meltdown has to do with out-of-order execution. Spectre has to do with speculative execution. These are two things that GPUs do not have. GPUs do not have out-of-order execution. They have in-order pipelines. GPUs do not have speculative execution. They don't do branch prediction. So there's no threat of Spectre or Meltdown on a GPU. That's more just, people learned some words after Spectre and Meltdown came out, got scared and they thought, hey, I've seen a GPU in a computer before. It does things. Yeah. People went a little bit crazy with Spectre and Meltdown. I mean, it's an interesting thing. It's amazing that people aren't more concerned about software vulnerabilities. I personally am far more worried about buggy software than I am some niche exploit in hardware, especially if software doesn't get patched. But nah, people will take some huge, maybe not huge, they'll take a significant impact on performance. They'll take some significant impact on performance for a hardware patch compared to, any amount of performance loss from a software patch. Makes you chuckle a little bit. All right. Anyone have any general programming questions or anything? Or are we going to call it a day? So you guys let me know what you guys want to see. If you guys want to see more GPU programming, let me know. If you want more general purpose programming, let me know. If you guys want computer architecture problem solving, let me know. I'll do what you guys want to the extent of what I want to teach. All right. If there's no more questions and there's no more comments, I want to thank you guys for joining me today. I had a lot of fun. You have a question? I'd be more than happy to answer the question. Oh, that wasn't a very nice question. ArcSats. Did you join us for the stream today, or did you just get here? I'm curious. You just got here? We just wrote CUDA code. Let's see. There we go. I always have to fix the audio when I go to this screen. Okay. Well, that's all we got today, though. If you guys have any specific topics on GPU programming, GPU architecture, computer architecture, and you want to send them to me, you guys are here right now. You can message me. I've got my Twitter and my YouTube linked below. I'll probably make some dedicated teaching content eventually for YouTube. And I'll probably do some more dedicated problem-solving streams. Thanks for sharing your knowledge. Hey, no problem, man. I'm happy to. But yeah, if there's any dedicated stuff, yeah, just always send it to me. I'm always happy to do dedicated stuff. I just kind of wing it as far as when it comes to teaching this stuff. If you actually want a book on learning this stuff, this is a good one. Programming massively parallel processors. It's kind of the gold standard for GPU programming. I've been through this. It goes through a lot of examples, a lot of ways to approach problems. It goes to what's it called? It has case studies in the back. It talks a little bit about OpenCL, honestly, as well. But it also has things like, I think it has you implement like convolutional neural networks, which is interesting. If you want the an intro book in computer architecture, if you're just starting out, there you go. Computer Organization and Design. A nice Hennessy and Patterson and Hennessy book. If you're a little bit more advanced in computer architecture, may I suggest the second book, Computer Architecture, A Quantitative Approach. Again, Hennessy and Patterson. And then, if you're already advanced in computer architecture, you've got to go with the one, the only, Parallel Computer Architecture. I picked up my copy today. Very nice. Very complicated. This is basically the final book in computer architecture. That is the capstone book, so to speak, as far as learning all this content. But, like I said, message me, shoot me a DM on Twitter or something, leave a comment on a Facebook thing or not a Facebook thing, a YouTube video. I think you can also email people through YouTube as well because it's Gmail. If you have a specific topic you want me to cover, other than that, thank you guys for joining me. I had a fun time today. We'll be back tomorrow, 5 p.m. Eastern Time. We'll do some more GPU programming, or if someone sends me something, we might do that. Or if I can look up some computer architecture problems, we'll just do maybe a stream of problem solving. All All right. I'll see you guys later. Adios.